the review of refrigeration and air conditioning is seen, and you have seen what are the various chapters or units in that. And in that refrigeration, so there is natural methods are also there and also mechanical methods are also there. So let us start the first unit.
Check, check.
So as we have seen, refrigeration may be defined as a process of removing heat from a body or an enclosed space so that its temperature is first lowered and then maintained at the required temperature. So always that temperature maintained will be lower than that of the atmosphere. So according to R&A, they define this as the science of providing and maintaining temperatures below that of surrounding atmosphere. So the system is maintained at a lower temperature compared with the atmospheric temperature. Okay. So the space where it is maintained is called as the refrigerated system. Okay. While the equipment used to maintain this lower temperature is known as the refrigeration equipment. So work is required to transfer heat from lower temperature body to higher temperature body. So whereas in a heat engine, so we are making use of the available heat source. Okay, with that we can able to get some work done. Whereas in the refrigeration system, we have to maintain lower temperature. So for that, it needs some work. So amount of heat removed by refrigerating equipment from refrigerated system is known as the refrigerating effect or the cooling effect required or the heat abstracted from the space to be refrigerated. And the effectiveness of the refrigeration or the refrigerator is measured in terms of the coefficient of performance. So coefficient of performance is defined as the ratio of the heat abstracted from the system to the work input given to maintain that system. So again, this is a process of removing heat from a space or a substance to reduce and maintain temperature lower than its surroundings. And when you see the history of this, so let us see 2 or 3 slides only on the history, how the refrigeration was developed and what are the various types of refrigerators. So before finding of mechanical refrigeration, natural phenomena was used. So that is nothing but ice. So ice from lakes and rivers during winter was stored and that was used for refrigeration. And which was that ice was stored in sawdust and used for cooling applications. And if you see the very old times, biblical times, the Romans harvested ice from mountains and used for cooling emperor's drinks. And in Middle East and India, water is cooled by evaporating it through clay pots. And in favorable conditions, it could be made cold enough to form ice. And again, see the history. In the year 1748, first mechanical refrigeration process was started by William Cullen. He investigated the refrigeration by evaporating ethyl ether into partial vacuum. And in 1834, Jacob Perkins presented cold cycle refrigeration system using compressor. And if you see the Jacob Perkins first model, so how the refrigeration was done, you can see the figure and the working given. So the refrigerant used was ether. So boils in evaporator. So that evaporator is given as B. So B in the first figure inside A. So the pump away from the compressor and it compresses to higher pressure at which it can condense to liquids in tubes D. So tubes are that is in the second vessel. So giving out heat to water in the vessel E. So condensed liquid flows through the weight loaded valve H. So H is in between the two vessels here. So which maintains difference of pressure between the condenser and evaporator. And the small pump above H you can see that is used for charging the apparatus with the refrigerant. So this was the model which was discovered by Jacob Perkins 1834. Again, if you see the history, in 1850, John Hague made Perkins' design into working model with some more modifications. Then this is the Perkins machine and the earliest vapor compression system used with either sulfuric or methyl ether as the refrigerant. And again after 10 years, John Gorey developed air cycle plant to make ice to cool air for circulation through his hospital in Florida. So you can see the figure. That is a Perkins machine built by John Hague. And in 1859, Ferdinand Care developed vapor absorption system by ammonia water cycle. So that is the model. Then afterwards, so France developed carbon dioxide based vapor compression system in Germany in 1886. So the carbon dioxide system is a very safe system and was used in ship refrigeration until 1960s. Then Raoul Piquet used sulfur dioxide as refrigerant, so its lowest pressure was high enough to prevent the leakage of air into the system. So because here the refrigerant is not going out of that system, so it was used for some time. Then Thomas Midgley and Han discovered dichlorofluoromethane, Freon, as super refrigerant. So with the add of Freon, then the actual refrigeration system was developed. Then generic electric company introduced the first domestic refrigerator in 1911. The initial domestic refrigerators used mainly sulfur dioxide as refrigerant, and generic electric company introduced the first refrigerator with a hermetic compressor in 1926. So hermetic compressor was used for refrigeration only from 1926, and these refrigerants were replaced by Freon 12 in 1930s. Let us go into the refrigeration part. So the unit of refrigeration is given by ton of refrigeration, or simply TR, represented by TR means ton of refrigeration. So ton of refrigeration is defined as formation of 1 ton of ice from and at 0 degrees of water within 1 day of 24 hours. So again I am reading, so the definition should be very clear. 1 ton of refrigeration is defined as the formation of ton of ice. So that ton is represented in terms of British units. So the ice was formed at 0 degrees centigrade when the water is again taken at 0 degrees centigrade, and it is done in a period of 1 day or 24 hours. So 1 ton of ice means 2000 pounds, which is equal to 909.1 kg, and because the latent heat of ice is 335 kilojoules kg, so the amount of heat removed from 1 ton of water to get 1 ton of ice is nothing but, so 9.1 into the latent heat 335, so which is converted into seconds. So divided by 24 into 3600 gives 3.516 kilojoules per second, or it can be approximated as 3.52 kilowatt. So 1 ton of refrigeration is nothing but the amount of heat removed. How much amount removed? So that is nothing but 3.52 kilowatt of heat removed from water. So mainly systems are divided into two types. So one is work absorbing system, then the other is work developing system. So work developing systems means some work is developed from that process. For example, if you take a heat engine, so if the heat is given, and here if the expansion is taking place in a particular engine, it will give out some mechanical work, or that can be again converted into electrical work. So heat engine is nothing but a work developing system. If you take work absorbing system, so refrigerator, the main function is to maintain the temperature lower than that of atmospheric temperature. So according to second law of thermodynamics, so heat can flow only from higher temperature body to lower temperature body only. So if the reverse is required here, then always some work is required. So refrigerator, heat pump, all these comes under the work absorbing systems. So the first figure you can see, so that is an engine. The top one is the heat reservoir. So where the heat is supplied in terms of, it may be steam or otherwise maybe the chemical energy produced in an IC engine, anything it is. So with that, with the expansion in turbine we can get some work, or with the expansion in the engine we can get some work. So that is a work developing system. If you see the right one, so here the cold reservoir. So the cold reservoir is the reservoir that is to be, or the space to be cooled, or space to be refrigerated. So that is done only by giving some work input. Okay. So the second one is called as a refrigerator or a heat pump. So some work is given for maintaining lower temperature. Okay. And that heat taken away from the cold reservoir is given to the atmosphere. So that is given, that is done by means of giving some work in. So if you see the efficiency of heat, so that is nothing but the work done by the heat supplied. Okay. So whereas EOP of the refrigerator is nothing but the cooling effect produced in the cold reservoir by the work input. So let us go to the air refrigeration system. So this is one of the earliest method, and here air is the refrigerant. So absorption of heat and removal of heat to the atmosphere, everything is done with the fluid air itself. And nowadays this is obsolete due to low coefficient of performance, and also it requires high operating cost. So mainly air refrigeration is mainly preferred in aircraft refrigeration. So where here, so lot of scope is there always for air refrigeration in aircraft refrigeration, because aircraft will be moving at high pressure. So with that we can able to get the required refrigeration or air conditioning in the aircraft. So let us see aircraft refrigeration in the next class. So the main characteristic of air refrigeration system is, so throughout the cycle air is not changing its phase. If you take the refrigerant freon, so it can alternately change its phase. Okay. So while taking heat, it will come out as vapor. So while giving out heat, it will be converted into liquid state. So in air refrigeration, there is no phase change. So that's why there are number of disadvantages are also there. We'll see all these later. Main air refrigeration is divided into two types, as a closed system and open system. So open system means here, so whatever the work is given out here, the fluid will go into the atmosphere. Whereas in the closed system, so the fluid is circulated throughout the cycle. And in the open system, air expansion to atmosphere pressure, so which can be done up to atmospheric pressure. Whereas in the closed cycle, so here the expansion can be done above the atmospheric pressure. We'll see open system and also closed system in the next class. So the various components required for refrigeration. So compressor, condenser, expansion valve or expander and an evaporator. So in this case, so whatever the work given out in the compressor, so with compressor the air pressure and temperature will be increased, and here because we require pressure at high pressure, so here the fluid is condensed in a condenser. Afterwards the air at high pressure and low temperature, when it is expanded in a valve or expanded in an expander, we will get the refrigerant at very low pressure and temperature, which can take the heat from the space to be cooled or space to be refrigerated. And here while condensation, so the heat given out will be QH. So while the refrigerant going into the space to be cooled or refrigerated here, so some heat is taken away from that space, so that is QL. Then mechanical refrigeration. Mechanical refrigeration system based on the principle of absorption of heat to fluid as it changes its phase from one phase to another phase. So vapor to liquid or liquid to vapor. So that is done by means of mechanical means like vapor compression system or vapor absorption system. So vapor compression system it requires high grade energy, whereas low vapor absorption system it requires low grade energy. So we will all see this in the second unit, vapor compression system and all this. So refrigerator is is nothing but a reversed heat engine or reversed heat pump, so which takes heat from a cold body and delivers it to a hot body. So the function of refrigerator and heat pump both same, but the function of refrigerator is to maintain the temperature than the atmospheric temperature, whereas heat pump means so water it will maintain at a higher temperature. The refrigerant is a heat carrying medium, so which during their cycle in refrigeration system absorbs heat from a low temperature system and delivers it to a high temperature system. So the refrigerant may be air, maybe neon, or maybe ammonia. So it may change its phase or may not change. So in air refrigeration, there is no phase change for the refrigerant. So whereas in vapor compression system, so refrigerant will alternately change its phase. So let us see the various applications of refrigeration. So mainly for ice making. So if you see the cost involved, if you compare in USA, nearly 30% of the amount is spent only for maintaining refrigeration and air conditioning. So that much of importance is there for refrigeration and air conditioning. So for ice making, transportation of food items above and below freezing. So because Kakinada is having seaport, so you can know what is the importance of seaport and all those. So the fish, prawns, everything will be imported. So that will long for even 1 year also. So that food can be stored for 1 year. Even after 1 year also they can use that for cooking. So that much importance is only with the refrigeration. Then industrial air conditioning and also for comfort air conditioning. For the comfort of the human beings always the temperature is important, then relative humidity, all these are important. So for comfort air conditioning that depends upon the season of the year or the location of the country, everything. Then chemical and related industries. So for making of the chemicals, so always this air conditioning is also required. Then medical and physical instruments for making of this and also for making operations. So this plays a vital role. Processing food products and for beverages and also for oil refining. So the temperature is to be reduced. Then synthetic rubber manufacturing, manufacture and treatment of metal. So for manufacturing also, you know, different metals are having different melting points. Okay? The melting point if it is very low, so it can be manufactured at very low temperature. So that comes under refrigeration and air conditioning. Then freezing food products. Then manufacturing solid carbon dioxide, production of extremely low temperature. So for maintaining very low temperature, so that science comes under cryogenics. Then plumbing and also building construction. So these are the various applications of refrigeration and air conditioning. Then if you see in detail the applications, so comfort air conditioning in auditorium, hospitals, residences, hotels, offices, classrooms. So all this comes under this one. Then manufacture and preservation of medicines, surgery. So surgery is to be done at a place that everything is comfortable. Then storage and transportation of food stuff. Okay. So the truck should be maintained with very low temperature to transport the meat or fish, whatever it is. Then manufacture of ice, processing of textiles, then cooling of concrete for dams, production of rocket fuel. So rocket fuels also require this air conditioning. Then for computer functioning also air conditioning plays a vital role. So why air cycle systems are used? Why air refrigeration has importance? So it is having specific advantages because here the working fluid or the refrigerant is air itself. Okay? So it is freely available and it is also safe, non-toxic, even though there is leakage is there, it doesn't hurt. So air cycle equipment is extremely reliable, reducing maintenance costs. So if you see vapor compression refrigeration, so the cost of the refrigerant itself is high, okay? And also the leakage should be completely prevented. So there is no such problem with air refrigeration. So when operating in refrigeration cycle, an air cycle unit can also produce heat at a useful temperature. If this temperature is used together with the cooling, highly efficient low energy processes are possible. And heat can be produced at a useful temperature which if it used together with the cooling can result in highly efficient and low energy process. So why air cycle refrigeration or air refrigeration has importance is mainly we can get the required COP and also because air is freely available we can make use of and it is also non-toxic safe also. So in this, the basic elements required for refrigeration is compressor, then heat exchanger or a condenser, then an expander. Expander is the device in which expansion takes place, and then refrigerator or the evaporator. So it is again of two types: open system and closed system. So in the open system here, the air used is thrown into atmosphere, whereas in the closed cycle, so the same air is continuously recirculated by passing through a cooler. So let us see the advantages of air refrigeration system. So as air is easily available compared with other refrigerants, so it is cheap. Already we have seen it is also safe. Okay. The air is non-flammable, so there is no danger of any fire hazard as that possible with ammonia, argon, and all this. Then the weight of the air refrigeration system per ton of refrigeration is quite low compared with other refrigeration systems. So that's why this is mainly used in aircraft refrigeration. So let us see the ideal cycles of air refrigeration. So always the ideal cycle of refrigeration is the reversed Carnot. So already you have studied Carnot cycle for a heat engine. So you know all the four process. So the same thing here because here so the space is to be maintained at a lower temperature. Some work is given. So the Carnot cycle used for refrigerator is nothing but the reversed Carnot cycle. What is used in a heat engine. So reversing the Carnot cycle does reverse the directions of heat and work interactions. A refrigerator or heat pump that operates on the reversed Carnot cycle is called as a Carnot refrigerator or Carnot heat pump. The reversed Carnot cycle is the most efficient refrigeration cycle, operating between two specified temperature levels. So it sets the highest theoretical COP. So the cycle used here is the reversed Carnot cycle. So the direction is only changed. So why the direction is changed here? Because we have to maintain the space at a lower temperature. For that we are giving some work input. And work done in the expansion is very less compared with the work done in a heating. So this is the diagram showing the reversed Carnot cycle, which is the most efficient refrigerator. So you can see the flow diagram. Okay, below this you can see the flow diagram. So the main components required in this is a compressor, then a condenser, then an expander. Expander may be called as a turbine or maybe an expansion valve where the expansion is taking place, and then an evaporator. So in the compressor, the refrigerant coming from the evaporator is compressed. So in the compressor, the temperature and pressure of the refrigerant will be increased. And when the high pressure, high temperature refrigerant goes into the condenser, so where condensation is taking place at isothermal. The process involved in this is isothermal condensation. So the temperature is maintained constant, but here, what is done here? Isothermal. Okay. So here condensation is taking place at constant temperature. Then when it is going into the turbine here, where expansion is taking place, and it is assumed as isentropic expansion. And then when it, because the refrigerant coming from the expander is at low temperature and pressure, so that can take the heat from the space to be refrigerated. So like that, the refrigerant will take out the heat from the chamber to be cooled or from the chamber to be refrigerated and goes into the again into the compressor. So the reversed Carnot cycle is the most efficient refrigeration cycle, operating between the two temperatures TL. TL is the lower temperature in the cycle and TH is the maximum temperature in the cycle. So however, it is not suitable model for refrigeration cycle since the processes, you see the processes 2, 3 and 4, 1. So 2, 3 is compression and 4, 1 is expansion. So which are estimated as isentropic process, reversible adiabatic process. So whereas the process 2, 3 involves the compression of a liquid vapor mixture which requires a compressor which will handle two phases. If you see the process 2, 3, 2, 3 in the TS diagram, so 2 is nothing but the inlet of the compressor, the refrigerant is at a low temperature and pressure also. Okay. So that will be compressed in the compressor. 2, 3. So involves the expansion of high moisture content. So in the air refrigeration, air is not changing its state. Okay. So that curve given in the TS is not having any significance. Just the TS diagram is represented by a rectangle. So without the curve, straight line and the solid line. And the reversed Carnot cycle, you can find out the COP of the refrigerator. COP of the refrigerator you can find out. So that is nothing but the refrigerating effect produced in the evaporator divided by the work input. Okay. So the refrigerated effect produced is represented by the process in the TS diagram 1 to 2. So the area under 1 to 2 represents, if you take S2 is the isentropic, S2 is the specific heat at 2 and S1 is the specific heat at 1. So the area under the curve 1 2 1 2 shows, so S2 minus S1 into lower temperature. So that is EL into S2 minus S2. So that is the numerator. So whereas the denominator is nothing but the work input. So work input is given by the area under the curve 1 2 3 4 1. So that is again represented by the difference between the two temperatures TH minus TL into S2 minus S1. So if you take the numerator and denominator for finding COP of the refrigerator, so you will get the relation as TL by TH minus TL. So which can be again, TL can be taken into the denominator and it can be expressed as 1 by TH minus TL minus 1. So that is the relation for COP of the refrigerator and COP of the heat pump. So in the same way we can find out COP of the heat pump, which is equal to 1 by 1 minus TL by TH. So both COPs increase as the difference between the two temperatures decreases. That is, if you see the COP of the refrigerator, so that is TL by TH minus TL. So when TL increases, so what will happen? So COP increases. So similarly, if TH increases, then also COP increases, because COP, it depends upon TL, so which will be in the numerator and also in the denominator. So TL is having more significance compared with that of the TH. So to maintain the refrigerator according to the required temperature, so the refrigerant coming from the expander should be always lower than 0 degrees centigrade. So if it is lower than 0 degrees centigrade only, we can maintain the evaporator at 0 degrees centigrade. So similarly, so if 3 is nothing but TH. So if TH is greater than atmospheric temperature, then only heat can be rejected into the atmosphere. But that is also not possible. So we cannot reduce the refrigerant coming at 1 below 0 degrees centigrade, and also we can take 2 at a temperature more than the atmospheric temperature. So all this depends upon the two temperatures, lower temperature and the higher temperature. So COP mainly depends upon TL by TH minus TL. So always TL and TH should be converted into Kelvin for finding the COP for problem. So the same flow diagram given in a simple way. So you can see the four components here: compressor, then condenser, expander, and then an evaporator. So again the TS diagram is drawn. So this without curve. So there is no significance for solid line and also the liquid line. So again, to increase the COP, TH should be kept low, but it cannot be reduced below 25 degrees centigrade, which is the atmospheric temperature, and TL should be kept high, but it cannot be increased above 0 degrees centigrade. That is the required temperature required in the evaporator or the refrigerator. So the change in TL has more pronounced effect than that of TH. That is the maximum cycle temperature for the reversible Carnot cycle. So these are the practical examples of the reversible Carnot cycle. So if a Carnot refrigerator is used for making ice, so where the required temperature is 0 degrees centigrade, and also for making an air conditioning room, which is required temperature is 20 degrees centigrade in summer. So when the atmospheric conditions are 40 degrees temperature, 40 degrees centigrade. So in that case, always the Carnot refrigerator used for AC plant will be having more COP than that of the refrigerator, because here So the COP is nothing but TL by TH minus TL. So for making refrigeration for AC plant, the required temperature is 20. So numerator is 20 plus 273 by the difference between the atmospheric temperature and the required temperature. So 40 minus 20, that is the COP for air conditioner. So whereas COP for refrigerator is the required temperature is 0 degrees centigrade. So 0 plus 273 by the difference between the two temperatures. So 40 minus 0. So always the refrigerator used for AC plant works more efficiently compared with that of the refrigerator. So in the same way, if you take B, for making ice, cornet refrigerator works more efficiently in winter than in summer. Why? Because in winter the temperature will be less, whereas in summer the temperature will be more. So in summer atmospheric temperature will be 50 degrees centigrade. So whereas in winter temperature will be 20 degrees centigrade. So with that, if you find out the COP in winter, so that will be 0 plus 273 by the difference between the atmospheric temperature and the required temperature. So 20 minus 0. And similarly, the COP in summer. So that is here is used for refrigeration. So where the required temperature is 0 degrees centigrade. So 0 plus 273 by atmospheric temperature minus required temperature. So COP in winter is always greater than COP in summer. Similarly, so AC plant having more COP compared with that of the refrigerator. So why Carnot cycle is not practical? So even though Carnot cycle is the most efficient cycle, so why it is not practical? So because it is having some undesirable characteristics. So what are these undesirable characteristics are? So isentropic processes require high speed. So isentropic compression in the compressor and isentropic expansion in the expander. So which requires very high flow rates of air. Then isothermal process. The two isothermal process. Heat rejection in the condenser, heat abstraction in the evaporator. So these require extremely very slow flow rate. So those two isentropic process should be at very high rate. So whereas the isothermal process should be at very low rate. So this variation in flow rate of air is not practical. So that's why Carnot cycle cannot be used as a practical cycle. It's only an ideal cycle. Then what are the theoretical cycles? So Bell-Coleman cycle is a theoretical cycle. Then reversed Carnot refrigerator. So the same thing with the flow diagram. Then the theoretical cycle used for air refrigeration is Bell-Coleman cycle. So you can see the Bell-Coleman cycle. Here also the components required is same: compressor, expander, heat exchanger, and the refrigerator. So that heat exchanger is nothing but a condenser here. So you can see here the warm air coming from the refrigerator is compressed in a compressor to hot air. Then the hot air here is passed through a condenser where heat rejection takes place at constant pressure. So whereas in the Carnot cycle it is assumed that heat rejection is taking place at constant temperature, but here it is constant pressure. So for heat rejection, cooling water is circulated through the heat exchanger. Then the cold air coming from the heat exchanger or the condenser is expanded in a expander. So in the expander some work is done. So that work is used for running the compressor, or it can reduce the work, extra work required by the compressor. Then from the expander, the expanded air, which is at low temperature and pressure, when it goes into the refrigerator, the space to be refrigerated, it will take the heat and finally it go into the compressor. And here also it is assumed as here in the refrigerator also The heat attraction or the refrigerating effect is also produced at constant pressure. So what? Please go with me. So the work gain from expander is used to drive the compressor. So that work is not at all sufficient to completely drive the compressor, but it can reduce the extra work required in the compressor. Hence, less external work is required. So Bell-Coleman cycle or the reverse Brayton cycle both are same. So again you can see the diagram showing the flow diagram. So compressor. So here at the compressor the inlet is at 2 and after compression here the refrigerant is coming at 3. When it is going into the heat exchanger it is coming at 5 and at 5 it is going into the expander. So you can see the various processes in the PV diagram and also the TS diagram. So in the PV diagram, if you see 1 to 2, 1 to 2 is nothing but suction of the refrigerant at the compressor inlet. 2 to 3. So 2 to 3 is nothing but the compression process in the compressor. So with that, so the pressure is increased and also if you see the volume is reduced. From the PV diagram, you can see 2 3 is nothing but the compression in the compressor. So it may be assumed as it is isentropic compression. But in actual case, it is not isentropic, but it will be a polytropic process. Then 3 4. 3 4 is nothing but the delivery stroke or the discharge from the compressor. Okay. Then 5 is nothing but the point where it goes into the expander. So 5 is the point here, that is the inlet to the expander. Then 5 to 6 is nothing but expansion in the expander. So with that expansion here, the pressure is reduced to again P1 and the temperature is also reduced. So at the point 6, it go at the point 6, you see the refrigerant will be at low pressure and temperature. When it goes into the evaporator, so that will suck the heat and it will make it cool or refrigerated. Then 6.2 is nothing but here the refrigerating effect produced or heat abstracted from the space to be refrigerated. So the same thing is given in the TS diagram also. So 2 is at the suction of the compressor. So 2 3 is the process. So that is assumed as isentropic compression in the compressor. And 3 5 is heat rejection in the heat exchanger or a condenser. This is assumed as constant pressure process. And 5 6 is expansion. Again it is assumed as isentropic expansion. So reversible adiabatic expansion. Then 6 is the point where the refrigerant is at low pressure and temperature. So that goes into the evaporator to be refrigerated. So 6 to 2 is the heat abstraction process or the cooling effect produced in the refrigerator by taking the heat from the refrigerator. So the same process are given in detail. So process 1 2 represents the suction of air into the compressor. Then process 2 3 represents the isentropic compression of air by the compressor. And process 3 5 represents the discharge of high pressure air from the compressor into the heat exchanger. Then the reduction in volume of air from V3 to V5 is due to the cooling of air in the heat exchanger. Then process 5 6 represents the isentropic expansion of air in the expander. Process 6.2 represents the absorption of heat from the evaporator. So which is assumed as constant pressure process. So always constant isothermal heat rejection will be always difficult compared with that isobaric process. So with this also you can find out the COP of the Bell-Coleman cycle. So that is the ratio of the refrigerating effect produced in the evaporator to the work input. So work input is nothing but the work required by the compressor minus the work done by the expander. So in the assumptions, the three assumptions we have seen is compression and expansion process are reversible adiabatic processes are isentropic process. Okay. But in actual case, these are not isentropic, but those will be polyphase. We'll see that later. There is a perfect intercooling in the heat exchanger. So it is assumed that that is at constant pressure. Then there are no pressure losses in the system. So these are the various assumptions in the Bell-Coleman cycle. So here also we can find out the coefficient of performance. So by knowing the refrigerating effect produced during the process is due to by the work input. So work done by the expander is, so see, you can see is here. So COP you can find out. So final equation I am seeing, that is the refrigerating effect produced in the evaporator by the work input. So work input is nothing but work required by the compressor minus work done by the expander. So here uh, the refrigerating effect produced is represented by Cp into T2 minus T6 during the process 6 to 2. So that is Cp into T2 minus T6. Then the net work required is work required by the compressor minus work required by the work done by the expander. So that is Cp into T3 minus T2. So that is the work input to the compressor. Then work done by the expander is Cp into T5 minus T6. So that COP you can see. So we can write this COP. So by striking off Cp, because Cp is common in numerator and denominator, we can strike off. Then the final relation for COP is T2 minus T6 by T3 minus T2 minus T5 minus T6. So the brackets in the right, first one is T5. So if you compare Bell-Coleman cycle with the reversed Carnot cycle, so the coefficient of performance is maximum with the reversed Carnot cycle. So that is nothing but this diagram. If you see, 1 to 2 is compression, 2 to 3 is heat rejection, and 3 4 is expansion, and 4 1. So in the previous figure the notation is different, and here you can see this notation. And here the COP for Carnot cycle is T1 by T3 minus T1, because that is a constant thermal heat rejection and constant thermal heat abstraction in the evaporator. So that is T1 by T3 minus T1. So similarly, we can also see the COP in terms of the two temperatures only. From the previous relation with the number of T's, we can get the COP of the Brayton cycle as T4 by T3 minus T4. So where that T4 is nothing but, so the refrigerant coming from the expander. So that by T3 minus T4. So that will be always less than COP of the Carnot cycle. Why? Because is T4. So even though T4 is at lower temperature, and similarly, so numerator is decreased. Okay. So instead of T1 here, it is reduced to T4. So that's why COP of the Brayton cycle is always less than the COP of the reversed Carnot. So whatever the Bell-Coleman cycle we have seen with the number of assumptions, isentropic compression, isentropic expansion, and isobaric heat rejection in the condenser, isobaric heat abstraction in the refrigerator or evaporator. So all the those are the assumptions made to analyze to find out the COP of the Bell-Coleman cycle. But there are number of deviations. Okay? So let us see the actual Bell-Coleman cycle. In the actual Bell-Coleman cycle, the compression and expansion. So these are not at all isentropic processes. Those are only polytropic processes. So with that, S will be always increased. So whereas in the isentropic process, so S will be always constant. So those are the deviations here, and also are the refrigeration. See here, one is at the compressor. So one to so that
Check, 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 check.
so if you see the actual Bell-Coleman cycle, one is at the inlet of the compressor and two is at the exit of the compressor. So so one two dash represented by the dotted line represents the actual compression process, which is not isentropic. Then similarly at so during the process 2 3 heat rejection, so it is not constant pressure heat rejection, but some pressure loss will be always there during condensation process. So due to that, P3 will be always lower than P2. And similarly during expansion process, so that is 3 4. 3 4 is represented by a solid line representing the isentropic expansion. But that is not possible, but it is shown by 3 4 dash, so which is a polytropic expansion in that. Also it is also seen that there is some pressure loss during the evaporation in the refrigerator also. So 4 dash, so you can see P4 dash is always greater than that of P1, so that pressure loss is taking place in the evaporator during heat abstraction in the refrigerator. So you can see the same with PV diagram also, how the volume changes, how the pressure changes. So let us see the advantages of air refrigeration. So some of the advantages already we have seen, because this is available in plenty, the atmosphere itself. So it is freely available refrigerant, and also the non-toxic and all this. So air is a cheaper refrigerant and available easily compared to other refrigerants which are costly and manufactured, and those are also scarce also. As air is non-flammable, there is no danger of fire or toxic effects due to leakage. the total system per ton of refrigerating capacity is less compared with other refrigeration systems, which is one of the major causes selecting for aircraft refrigeration. We'll see that in the next class. Then let us come to the disadvantages of air refrigeration. Then the quantity of air required per ton of refrigerating capacity is greater than other systems. The quantity of air required is always more compared with the other refrigerants. Why? Because there is no phase transfer taking place with this refrigerant. So whereas if you compare other refrigerants like freon or ammonia, anything, so during heat addition, it will be converted into vapor, and while taking the heat from the refrigerated space, it will convert into vapor. While condensing, it will come into liquid state. So that is not possible with air. Then the COP is low, and COP of the air refrigeration is always low compared with that of the vapor compression refrigeration or vapor absorption system, and also it requires high maintenance also. And there is a danger of frosting at the expander valves is more, as the air taken into the system always contains moisture. So because in the open air refrigeration system, so directly air goes into the evaporator. So because air is having moisture, always there is chance of freezing of the expansion valves within the expander. So that is not the case in dense air refrigeration. We'll see that in the next class. So this is the difference between open air refrigeration system and dense air refrigeration system. So I think you have heard a lot with the theory. Then you solve some problems, easy problems. From next class onwards, all of you come with the calculators. So for air refrigeration, calculators is sufficient. And when you go for vapor compression system, then refrigerant tables and charts are necessary. So you bring those to the next class. Then you take the problem, simple problem with a calculator, you can easily solve. Take the first problem. Heat is to be removed at a temperature of 5 degrees centigrade and rejected at a temperature of 35 degrees centigrade. So what is the Carnot or ideal COP? So Carnot cycle COP is the maximum. So even though it is asked as ideal cycle, then you can easily do this. So COP is nothing but the lower temperature by the difference between the two temperatures. So only thing is you have to convert degree centigrade to Kelvin. So 5 is the minus 5 is the required temperature. So 273 minus 5 by the difference between the two temperatures. So 35 minus 5. So that comes to 6.7. Then you can note down another problem. A refrigeration system produces 40 kg per hour of ice at 0 degrees centigrade from water at 25 degrees centigrade. Find the refrigeration effect per hour and ton of refrigeration. If it consumes 1 kilowatt of energy to produce the ice, find the COP. And you can assume that latent heat of solidification of water or fusion of ice at 0 degrees centigrade is 335 kilojoules per kg, and specific heat of water is 4.19 kilojoules per kg degree centigrade. So what is the COP required? And the other thing is, what is the tonnage? So first thing is you have to see that the water is at 25 degrees centigrade, and first it should be converted to 0 degrees centigrade. Okay, the total heat removal rate to 40 kgs of ice at 0 degrees centigrade from water at 25 degrees centigrade. So that you have to find out. So that is nothing but the sum of sensible cooling required from 25 degrees centigrade of water to 0 degrees centigrade plus the latent heat of fusion of ice. So here the mass is given as 40 kgs. So 40 kg power into the water is taken at 25 degrees centigrade and it should be converted to 0 degrees centigrade. So 40 into 25 minus 0 and you have to take specific heat of water. So mCp delta T. So that is nothing but the heat removed from water. So 40 into delta T into Cp. So plus again it is to be converted into ice. So that is latent heat of ice into again mass. So 40 kgs of ice is required. So 40 into 335. So that is the total heat removal rate from to form 40 kgs of ice from water at 25 degrees centigrade to 0 degrees centigrade. So if you calculate that, that will be 1,75,000 17,590 kilojoules per hour. So that is the refrigerating effect required, or that is the cooling effect required in the refrigerator. Then since 1 ton of refrigeration already we have seen that as 3.5 kilowatt, which is equal to 210 kilojoules per minute. So if you convert to kilojoules per hour, so this will be 12,600 kilojoules per hour. So to find out the tonnage required, so it will be, so the total refrigerating effect required by 1 ton of refrigeration. So that is 17,590 by 12,600 gives 1.39. So 1.396 is the tonnage required. So tons of refrigeration required. Then find out the COP. COP is the refrigerating effect by the work input. So work input is given as 1 kilowatt. So the numerator is already known. That is the refrigerating effect calculated as 17,590 kilojoules per hour. And the work input is given as 1 kilowatt. So 1 kilowatt should be converted into kilojoules per hour. So multiply 1 with 3600. So convert into hour should be converted to second should be converted to hour. So into 36. So that is COP is 4.886. So this type of problems will come in air refrigeration system, and also some problems on Bell column and cycle also important. So in this problem what is done here is, so water is taken at 25 degrees centigrade and it is to be converted to ice at 0 degrees centigrade. So you have to first find out the total heat to be removed or the total refrigerating effect required. Then you find out what is the tonnage of required. How many tons of refrigeration is required for converting this water to ice. Then find out CO. Then you can take another problem. So this is a still easier problem compared with the previous one. You can note down this. 200 kg of ice at minus 10 degrees centigrade is placed in a bunker to cool some vegetables. 24 hours later, the ice has melted into water at 5 degrees centigrade. What is the average rate of cooling in kilojoules per hour and tons of refrigeration provided by the ice? Assuming that the specific heat of ice is 1.94 kilojoules per kg degree centigrade and specific heat of water is 4.1868 kilojoules per kg degree centigrade and latent heat of fusion of ice at 0 degree centigrade is 335 kilojoules per kg. So what is the refrigerating effect required? You first to find out. So the rate of heat addition to 200 kg of ice at minus 10 degrees centigrade to water. So from water at 5 degrees centigrade. So first assume that the water is taken at 5 degrees centigrade and that is to be converted into ice at minus 10 degrees centigrade. So same as the previous one, here also mcp delta T plus m into L. So m is 200 and Cp of ice uh, Cp of ice is 1.94 and the difference between temperatures 0 minus 10. And here again ice is at 0 degree centigrade. So m into L plus again here what you have to consider here is again mcp delta T of water also. So because here in this problem, so the ice is at minus 10 degree centigrade, whereas in the previous problem the ice is to be formed at only 0 degree centigrade only. So with the addition of this you will get mcp delta T for ice separately and mcp delta T for water separately, and then ml should be added in both the terms. Only that is the difference between the previous one and this one, because ice is to be formed at minus 10 degrees centigrade, whereas in the previous problem what we have seen is the ice is required at 0 degree centigrade. Then that is you find out the capacity, that is 3127.78 kilojoules per hour. So to convert this in tons of refrigeration, so already we have seen that 1 ton of refrigeration is equal to 3.5 kilowatt or 210. So already we have done kilojoules per minute, or otherwise it is also equal to 12,600 kilojoules per hour, because the numerator is in kilojoules per hour. So you take the ton of refrigeration also in kilojoules per hour. Then you will get the ton of refrigeration required is 0.248. So we find the difference between the previous problem and this problem. So only you have to see the temperature required. So the ice is to be required at minus 10 degrees centigrade, whereas in the previous problem the ice is to be formed at 0 degrees centigrade only. So you can take this problem as a homework. We will see this problem in the next class. The problem is on the Bell-Coleman cycle. So for the Bell-Coleman cycle, so you have to know the two pressures required, and also you have to find out all the four temperatures. Then only you can get the required COP or ton of refrigeration required and everything. So you can note down this problem. A refrigeration machine of 6 tons capacity working on Bell-Coleman cycle has an upper limit pressure of 5.2 bar. So the maximum pressure given is 5.2 bar. The pressure and temperature at the start of compression are 1 bar and 18 degrees centigrade respectively. The cooled compressed air enters the expander at 41 degrees centigrade. Determine coefficient of performance, quantity of air circulated per minute, piston displacement of compressor and expander, bore of compressor and expander cylinder when the unit runs at 240 rpm and is double acting with stroke length 200 mm, and also find out the power required to drive the unit. So the inlet conditions or the suction conditions for the compressor is given as 1 bar and 18 degrees centigrade, and the maximum pressure is given as 5.2 bar. So P1 and T1 are given. So with P2 find out T2. Then it is also given that T3 is also given. The cooled compressed air enters the expander at 41 degrees centigrade. So T3 is known and also T2 is also known. So find out T4. So after finding all the temperatures, you can find out the COP. COP is the refrigerating effect produced by the work input. And also you can find out what is the quantity of, if possible, you complete the problem. Otherwise, you will discuss in the next class with some more examples. So in this problem, what we have taken here is, so compression and expansion are isentropic. And in some problem, the isentropic efficiency of the compressor may be given and isentropic efficiency of the expander may be given. So in that case, you have two more temperatures will be added. Okay? And in some problems, it may be given that there is a pressure loss during condensation and there is some pressure loss during evaporation.